Okay, so now we're going to move on to path integral quantization. And the reason why we're going to look at path integral quantization is I think that this is the most direct way to get to the Feynman rules. So I'm going to invite you to think about path integral quantization in a certain way. So to start off, you are familiar with this quantity. There's the vacuum time-ordered product of a product of n scalar fields. You know what the fields are. You know the mode expansion. You know Ket vacuum and Bra vacuum, how the creation and annihilation operators act on the vacuum state. You also know what the time ordering notation means. So you could go ahead and calculate this correlation function. Well, especially at the beginning, I'm going to invite you to think about the path integral formulation of quantum field theory as an alternative method to calculate this time-ordered correlator. You can develop more sophisticated points of view as you learn, but certainly at the beginning, I think it's useful to think that the path integral gives us a formula for these time-ordered correlation functions. And that formula is given by it's the path integral over all possible fields. So don't get scared. I'm going to have to tell you what this is. And then we've got e to the is, the action of the theory. And then we've got the product of our n fields. And I want to start telling you what actually the path integral quantization is. So first of all, let's come back to the expression that you know for the time-ordered correlator. So if you look at the left-hand side of this equation, and I ask you to tell me, well, what's the framework that you're using to do calculations? Well, I'm sure one of the things that you'll mention is this is a calculation that takes place in Fock space, the direct sum of Hilbert spaces with fixed number of particles. And we build the state by acting with creation operators on the vacuum. I think you'll also tell me that phi of x is an operator. And you'll tell me that you're doing quantum field theory. And that means you've got all of the normal things that go with a quantum theory, things like the uncertainty principle and things like that. And if I was to ask you, but how did you build the uncertainty principle into the theory? You'd tell me it's by using operators. So, for example, two operators that don't commute, they can't simultaneously have sharp values for their eigenvalues. And this is how you build in things like the uncertainty principle. Okay, so at that level, what do we mean by the path integral? Well, the interesting thing is this phi of x1 up to phi of xn that appears over here, all of these phi of xi's are ordinary functions. Okay? At the risk of laboring the point, they are not operators. In fact, on the right-hand side of this equation, there's no operator appearing anywhere. Now, this equation is going to hold both in the free theory and in the interacting theory, okay? So it holds when interactions are turned on. But for us, we're going to develop the path integral quantization for the free scalar field. And this means I'm going to integrate the 4x. Of course, you could do this in any number of dimensions. I'm doing it in 4 dimensions. Then we would have 1/2 d mu phi minus 1/2 m squared phi squared. So I'm just choosing the free action for now because that's the theory that we're familiar with. Later on, we are definitely going to add interactions. But then you might be puzzled. How on earth do we achieve quantization? Previously, we achieved quantization by promoting our fields to be quantum operators. So how on earth is quantization achieved here? So quantization is achieved. So quantization is achieved because we do the path integral over phi. If you study the operator formulation, to quantize each degree of freedom, you postulate a commutator. So if you say P comma X is equal to minus I H bar, you have quantized the degree of freedom. So for each degree of freedom that you want to quantize, you're going to want to have a commutation relation with this H bar sitting there. In the path integral, for every degree of freedom, each degree of freedom you quantize, you do the path integral over the degree of freedom. So now we're quantizing degree of freedom not by postulating some commutator, but by doing the path integral over that degree of freedom. So the quantization looks rather different. And now, what do we mean by this path integral? Well, the path integral over phi of x is defined to be the integral over the space of all fields. Now, I'm willing to bet serious money that you haven't seen path integrals over fields yet. So I want to develop these ideas, the idea of a path integral, in the simplest possible setting. And remember, when we were studying field theory, we went from a single particle to many particles to the field. I want to do something similar here. So in that vein, if that's the picture you've got in mind, that's the correct picture. I want to start off, and let's just remind ourselves, what do we mean when we say we want to perform an integral over the real numbers? So over R, just a one-dimensional real integral. So the way we would write it, we write a symbol, the integration sign, from minus infinity to infinity, f of x dx. And what is our space R? Well, here's the number line. You know, this point over here is 1. There's 0. This one is 1. That's 2. That's minus 1. So this is the space R. And let's just say one more thing about this space, because this will be a useful thing to think about for each of the spaces that we meet. If you want to pick a point in the space, what does this mean? This means you choose a real number, and we've been calling this real number x. Good. So now let's make a small generalization. Let's now study the integral over r to the d. What do we mean by this? Well, in this case, we've got an integral from minus infinity to infinity. Actually, we've got d of them. So we've got d integrals from minus infinity to infinity. We've got some function that depends on x1 up to xd. And then we've got dx1 up to dxd. Sorry, dxd. So let's just correct that. Good, dxd. Very good. So now if we want to visualize the space, well, we might draw something like this. Here is x1. Here is x2. Keep going. Here is xd. Okay. And if you do pick a point in the space, well, there's our point sitting somewhere. So we would project it down to the plane. Apologies for my art. And we would project here to get a value of x1, here to get a value of x2, and maybe along here to get a value of xd. I'm really sorry that picture's so bad. but hopefully you've got the idea. So you've got a point in this d-dimensional space, and then you project onto the different axes. That gives you a set of d real numbers. So if you want to pick a point in the space, so pick a point in the space means you must give d real numbers. So you must give me x1, x2, up to xd. Another way of saying it is you should give me xi or I from 1 to d. Good. And what you can see is this looks like we've just got d one-dimensional integrals. So this just looks like d one-dimensional integrals. So that's great. What have we done? We had the one-dimensional case, and now we've generalized it. We've generalized 1 to d, but d is still finite. We can do a much bigger generalization. We can generalize things so that choosing a point in the space is like choosing an infinite number of real numbers. Okay, and so the right way to think about it is this one-dimensional integral. This was like when you had the single particle. This d-dimensional integrals when we go to d particles, and now we want to go to the field. Okay, and this is going to be the infinite generalization. So now we're going to say integrate over the space of fields. So we still write an integral sign, and we write d phi. This is meaning integrate over the space of fields. We could have whatever integrand we want. I'm just going to write down e to the is, because this is pretty much always going to be our integral, our integrand. Okay, so I'll just write it down because that's what I'm nice and familiar with. And now let's talk about what choosing a point means. Okay, so choosing a point is choosing a field. But choosing a field is choosing a function phi of t and x. But that means you must give a real number. So I'm assuming I'm dealing with a real field. You must give a real number. Let's call that real number phi of t comma x for every t and x. Okay, so that's what it means to think about the space of fields. Each point inside the space is a function, and that means in exactly the same way in the d-dimensional case, each point is a set of d real numbers. Each point inside this space of all fields is actually an infinite number of real numbers, because you're picking a field. So you're picking a real number for each t and x. And then what that means is when you're doing a path integral, you're actually doing an infinite number of one-dimensional integrals. Okay, so I hope conceptually you're getting some idea of what a path integral is. So think about that. It's if it is a completely new idea to you, it'll take a little time to digest, and that's completely normal. And at this stage, it should not be clear to you at all why quantizing like this in the path integral method is anything like the quantization you know using operators in Hilbert spaces. And it's going to take me a little bit of time to convince you that the two are equivalent, but let's go step by step.